I've got two balls in my hand. I got a rubber ball and a much heavier brass ball. What I'm going to do is I'm going to roll them off the edge of this countertop, and I'm going to have you try to figure out two questions. Number one, which one do you think is going to hit the ground first? The lighter rubber ball, the heavier brass ball, or should they hit the ground at about the same time? Think about it. This room has very little air resistance, okay? So, use that information as you see fit. And number two, which one do you think will roll farther? If I give them both the same initial thrust, should one of them go further? All right, I'm going to go ahead and roll them off now, okay? Okay, so hopefully you are able to see that both the metal ball and red rubber ball fell at approximately the same rate. That is because this room has very little air resistance and only gravity should be affecting them when they are in free fall. Also, you should have noticed that they both landed at about the exact same place. That was because I applied the exact same acceleration to both of them. And if you can check with your displacement formula, you will know that if they both have the same acceleration, have the same initial velocity, and roll for the same amount of time, they should land at the exact same place. That is because of the displacement formula that we know, the fourth one. So, hopefully you're able to take away that they both fell at the same rate and landed about the same distance from the countertop as each other. Cool! So now we have this wonderful little device that can actually both launch a projectile and drop something at the exact same time. So my question to you is, which one do you think is going to hit the ground first? The projectile, the one over here, or the one that is dropped? The way you're going to tell is you're going to listen. You're going to have to use your ears for this one. You're going to listen to try to hear if they sound like two consecutive ball drops, or if they hit the ground roughly the same time, you should hear one continuous bounce, basically. Okay? Ready? Cool, we're gonna do that in slow motion as well. So here we go. Okay, so hopefully you're able to tell that both an object that is dropped and an object that is thrown perfectly sideways, if they are thrown from the same height, they should hit the ground at the exact same time. Why? Well, because of gravity. Since this room has very little airflow, then there's very little air resistance to stop these objects or slow either of them down. And as we know, that's the only reason that some objects appear to fall faster when we drop something compared to light objects like a feather. All it has to do is with air resistance. Without air resistance, we only got gravity. So even projectiles, if they're thrown perfectly sideways, then even the projectile should fall at the same rate as something else that is dropped. Okay? As long as, let's say, you're not having some sort of object obstructing the path of the ball, right? Like a body. All right. So, as you have seen all the different videos about projectile motion, let's put some actual definitions to it. Any projectile is an object with independent vertical and horizontal motions that move through the air only under the force of gravity after an initial thrust. So what that is saying is, when I'm describing independent, what I mean is that only gravity is acting on it downward, and there was some sort of initial force that caused something to go sideways. So like a baseball being hit by a baseball bat. Okay? The trajectory is the path that the projectile takes. These things are good to understand just for notes. As you can see down here in the bottom right, this raccoon is a projectile because it is being launched sideways, and the only motion that, or the only force that is acting upon it after it is launched is gravity itself. A projectile will accelerate at the same rate as a dropped object. What that means is it will accelerate downward due to gravity at the exact same rate. One thing that is a little tricky to understand about projectile motion is that the horizontal velocity doesn't change. It is constant the entire time. So the initial horizontal, so Vxi, is the exact same as the final horizontal. We describe vertical, so up and down, as y, and side to side, left to right, as horizontal, which is x. Okay? So in this x direction, the velocity stays the same as the initial force that it is given. We are saying this because we're assuming no air resistance. Obviously, if you've ever felt the wind resistance on your face, if you stuck your head out the window or hand out the window while driving a car, it feels immediately like your hand is being pulled backwards. That's because of air resistance. If there was no air resistance, it would feel the exact same in the car as outside of the car. Okay? So this right here means that initial velocity, I'll even rewrite it down here because it is that important. Initial Vx is equal to final Vx. It never changes. Vx never changes. Horizontal V, I don't know how many times I have to say this. Horizontal V, it is always the same. I don't know how many times I have to repeat this to make you write this down, but write it down. Horizontal velocity is always the same. Those are two ways to think about it. It never changes or always stays the same. As you can see, though, the y-axis, the y velocity is increasing over time. This is very similar to the dropped objects. In fact, it's the exact same. If you go back and look at previous videos, Vy is negative 9.8 after 1 second, and then it goes down by 9.8, then 9.8, increase by 9.8, and keeps going. After 5 seconds, we're at negative 49 in the downward direction. Okay? So only y is changing. Only y is accelerating. We have one more video to really just drive this home, and it's from the Mythbusters, so it's always a good time. So let's go ahead and watch that now.
Everything's hot. Let's do it.
And after a few test fires and a bit of fine-tuning, it works.
Pull it, please. Done. Oh, it's good. It's good. It's 1/3 of a millisecond difference.
Wow.
That's freaking perfect. Let's go do this full scale.
Okay.
All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, Jude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
The shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.